Hello, welcome to the 2024 ISNAF Young Investigator Franco Strazzabosco Award Symposium. My name is Andrea. I'm the director of the Photonics Initiative at the City University of New York Advanced Science Research Center, and I'm honored and glad to chair this symposium. ISNAF is the Italian Scientists and Scholars in North America Foundation, and our mission is to connect, empower, and celebrate the Italian intellectual diaspora in North America. We can count over 3,000 members in North America, and we're very active in connecting them across our chapters and promote networking, cultural, scientific, academic, and technological cooperation within our community and with public and private organizations in North America and in Italy. Today, we are holding this symposium to hear from the finalists of the Franco Strazzabosco Award. Generally, the ISNAF Awards fulfill our mission to celebrate the young investigators of Italian origin that work in North America. These Young Investigator Awards have the mission of celebrating in various disciplines the outstanding early career Italian researchers working in the United States or Canada in recognition of their significant and innovative contributions to their field of research. In particular, the Young Investigator Franco Strazzabosco Award was established in 2013 by the Strazzabosco family in memory of Dr. and Engineer Franco Strazzabosco. And this award is a tribute to the entrepreneurial courage of Italian engineers who strive to apply scientific discoveries to the public advantage. I want to introduce our jury, in particular, Professor Alberto Salleo from Stanford University. He has been for several years the chair of this committee, and I'm happy to help, and I thank him for guiding me in this. And Professor Matteo Rinaldi from Northeastern University that joins us on the jury. So today we will hear from the three finalists, and then we will convene as a jury, and we will select the winner of the award that will be announced at the annual meeting of the ISNAF next month. I think we can start with the program. The audience can ask questions in the chat. We welcome everyone that is connected, and I will coordinate the question time. So each panelist has 15 minutes to present their research, and then we will have 8 minutes of questions. So the first finalist is Dr. Claudia Cea, a postdoctoral fellow at the Massachusetts Institute of Technology, and she will present on conformable organic bioelectronic devices for health monitoring. Claudia, you can share your screen and
Yes.
the presentation.
Sure. Can everyone see my screen?
Yes.
Okay, perfect. Let me try, see if I can switch slides. Okay, all good. Good morning, everyone. It's great to be here. I am Claudia Cea, and I'm currently a postdoc in the bioelectronics group led by Polina Nikeva in MIT. Today, I'll talk a little bit about my work on conformable organic bioelectronics for health monitoring. Before starting, a little bit about myself. I was born and raised in Italy, where I got my undergrad degree in biomedical engineering. For my master's degree, again in biomedical engineering, I moved to San Diego. And in 2018, I switched to electrical engineering for my PhD at Columbia University, working on neural interfaces for electrophysiology. Almost exactly 1 year ago, I started my postdoc here in MIT with Professor Polina Nikeva, working on devices for gut electrophysiology. And starting from July 2025, I will be an assistant professor in the electrical engineering department at Yale University. But enough about myself, let's dig into the presentation. And let me start by introducing what is bioelectronic medicine, which is the title of this talk. It is a new field that focuses on developing methods to treat diseases using electrical pulses instead of drugs. This bioelectronic medicine is based on the idea that the central and the peripheral nervous system operate through electrical signal. And by harnessing this knowledge, electrical stimulation through an implanted device can be used as a targeted treatment modality in the organ of interest. Usually in Hollywood movies, it's always the bad person that wears bioelectronics or in general prostheses that are controlled by the brain, when the reality is much different and much closer to what we see here on this picture on the right, which is a child with a cochlear implant that was born deaf. And thanks to this little device that can stimulate the cochlea, his hearing is restored. I find very interesting that since ancient times, people have been captivated by electricity and its potential for therapeutics application. It's reported that some ancient Egyptians would stand on electric fish to control pain, or that some ancient Greeks would use electric rays, which is a type of fish, to treat physical and mental disorders such as epilepsy or vertigo, and also to numb the pain of surgery and childbirth. But arguably, the field of bioelectronic originated from the work of Luigi Galvani in the 18th century, when he performed the famous experiment with the dead frog, applying electricity and getting the legs to twitch. And around 200 years later, the first implantable pacemaker was developed by Bakken, which was also the co-founder of Medtronic. And from that very first pacemaker, a lot of different bioelectronic devices were developed over the years. This is not a comprehensive list, but just to give an idea, all the different type of bioelectronic devices that are there. And beginning in the 2000s, neuroelectronic devices started to be developed, and we see the rise of neuroelectronics, which is my research area. But what is a neuroelectronic device? It's something that, if it's implanted in the brain, can continuously monitor brain activity, identify biomarkers for local and responsive delivery of intervention, and can transmit data, the recorded data, outside of the body for evaluation of the treatment's efficacy. These systems are currently built using silicon-based transistors, which are the fundamental building blocks of modern electronics. We have millions, if not billions of them in our phones, in our computers, but there are some concerns related to this electrical component for what regard the power demand, the environmental footprint, and most importantly for this specific type of application, which is neuroelectronics, mechanical mismatch, and biocompatibility. But let's analyze these concerns one at a time. So, as I mentioned, these transistors are essential for the operation of these devices. They function as switches or amplifiers controlling the flow of electricity within circuits. They power the microprocessor and the sensors in these devices, but as the circuits incorporate millions of transistors, the power demand is significantly high. For instance, an OpenAI ChatGPT-3 model that tries to simulate and reproduce brain function requires about 1.3 gigawatt hours. And in stark contrast, the human brain only operates at just 12 watts continuously. So this difference in power highlights the importance for developing brain-inspired electronics that would achieve far greater energy efficiency and low power computing solution. A secondary concern for silicon-based electronics is the fabrication energy cost. Chip fabrication or semiconductor manufacturing in general is one of the most energy-intensive processes in the world. The power consumption of a semiconductor fabrication facility can be enormous, up to 100 megawatt hours. And just to get a practical sense, a typical chip fab will use as much power in 1 year as about 50,000 ohms, or as is displayed in this slide, an average chip manufacturing today uses 10 million gallons of ultra-pure water per day, which is as much water as is used by 33,000 US households every day. And the main driver of this high power consumption in the chip fabrication is basically the reliance on high temperature processes, which operates usually around 700 degrees Celsius. So to address this, we need alternative solutions that are centered around easy to fabricate devices, such as solution-based electronics that can be also processed at room temperature, and that can potentially reduce energy consumption and environmental impact. And the third concern, which is the most important for my research area, which is neuroelectronic devices, is the fact that these silicon-based transistors are rigid by nature. And due to this fact, there is a big mechanical mismatch between the implanted device and the neural tissue, and this can cause implant failure or lead to an inflammatory response. Also, these silicon-based transistors, this chip, have to be encapsulated in bulky metallic boxes to avoid contact with body fluids, and this minimizes their usage as wearable and chronic electronics, and in general decrease their biocompatibility and their duration in the body long term. So as an alternative, we can generate transistor that mimics the brain for both what regard the softness and the power consumption, and that are also more environmentally friendly. A solution can be organic electrochemical transistors that are inherently soft and conformable due to the fact that the transistor channel is a conjugated polymer, which is basically a solution, as we can see in this image here, that can be spin-coated on two different substrates, from flexible to stretchable, making the fabrication of this transistor low cost and without the need of any complex and high temperature process. On top of that, this transistor can operate at low voltages, typically around 0.5 volt, while still maintaining an impressive signal amplification properties, which are very important if you want to record low amplitude biosignals. So as my research goal is to build next generation neuroelectronic devices that are both more organ-friendly, but also environmentally friendly, I use these organic electrochemical transistors as building block for each device component, including the front end, the processing unit, and the wireless communication, with the final goal of creating a fully flexible, implantable neuroelectronic device, which is highly biocompatible and without the need of any rigid or silicon-based component. So starting from the front end, which is the device part that is in direct contact with the neural tissue, I use these organic electrochemical transistors, or just shortly OECTs, to build conformable neural interfaces based only on conductive polymers and on thin film plastic substrates for a total thickness of around 3-4 micrometers. As we can see from these images, these neural interfaces can perfectly conform on different biotissue, from the neural cortex to the palm of the hand. All the materials involved in the microfabrication of these devices are not only highly biocompatible, but also FDA approves. So for this reason, this technology is suitable for translational studies. And as I mentioned earlier, they can be their production is cost effective, and they can be easily reproduced at room temperature. So I use these neural interfaces to acquire and record a wide range of biosignal with a signal-to-noise ratio higher compared to commercially available metal electrodes. As a matter of fact, I was able to record EMG signal from muscle, ECG from hearts, local film potentials from group of neurons, and action potential from single neuron, which is the highest, which is a signal with a very high spatial resolution, spatiotemporal resolution. Transitioning to the acquisition and processing unit of the device, which is responsible for amplifying and processing the acquired signal, I used this type of transistor, and I was able to improve their performance in terms of speed and crosstalk. And I was also able to scale down the dimension of this transistor from a micrometer to a nanometer scale. This allowed me to integrate 1 million of this transistor into a small few centimeters squared area, while still keeping the high flexibility and conformability of these devices. And I use them to build different circuits useful for neuroelectronic devices, such as amplifiers, oscillators, or multiplexers. And I also developed, yes. Okay, yes, and I also developed a rectifier for real-time detection of epileptic discharges in vivo. Usually, this is something that is done using previously acquired data. In this case, this rectifier based on this transistor can real time can detect in real time this high amplitude peak, which represent the epileptic activity that we can see here in this red line. While in the black line, we have just the raw signal that is recorded. Finally, I integrated this system with a flexible ion-based wireless communication technology that allow me to power and transmit the data with the implantable device through an intact tissue at distance. This technology is called ionic communication and leverages the presence of ions in our body to transmit signal. The concept here is that if we have two pairs of electrodes separated by an ion-rich media, and if we send a low amplitude signal voltage from the transmitter, this signal can be read at the receiver thanks to a change in the electric potential energy. So for the first time using this technology, the whole wireless system was composed entirely of soft components. And I use this ionic communication, as I mentioned earlier, to both power at distance my implanted device through an iron-rich media, such as the skin. And I was also able to transmit the data to an outside computer. Just as a reference, I displayed here the fully flexible implanted device that I developed. As we can see from the image on the left, it is only a highly flexible plastic-based wire, where on one side we have the transistor that are responsible for the signal recording and for the processing of the signal recorded, while on the other side we have these three flexible gold contact electrodes that were laminated on the skull and were responsible for the data transmission and for the powering of the implanted device. While on the right, we have a traditional implanted neuroelectronic device that, as we can see, has different rigid components, such as batteries, silicon-based amplifiers, also cables. In my case, for the first type, I developed the first prototype of a fully flexible implantable neuroelectronic device based on this type of transistor without the use of any rigid component at all. And of course, I use this fully flexible platform to record high-quality neural activity in vivo chronically a few weeks after implantation. So with this presentation, I hope that I've convinced you that it's possible to build neuroelectronic devices that are not only more organ-friendly, but also more environmentally friendly, using this type of transistor that requires low voltages, that can be processed at, that are easy to fabricate and that are solution-based and can be processed at room temperature, and that are soft and conformable by nature, since the material of this transistor, the channel material of this transistor is a conjugated polymer. So thanks to this transistor, I was able to develop the first prototype of a fully flexible implantable neuroelectronic device. And thanks to this work, I was featured this year in the MIT Technology Review, 35 Innovators Under 35 globally. But of course, all this work was possible only thanks to my amazing advisors, Professor Dion Kodagolis at Columbia University and Professor Polina Nikevas here in MIT. And of course, thanks to all of my amazing lab mates that are also my great friends and all the funding agency. But most importantly, I want to thank each of you for your attention. If you have any question, I'm glad to take it. Thank you.
Great. Thank you, Claudia, for the great presentation and also for staying on time. And I encourage the audience again to write questions on the chat, and also the jury members if they have questions. Maybe I can start, Claudia. Oh, sorry.
Oh, no. I was just going to say, do we can ask our questions, right? We don't need to write in the chat, right? Okay. Well, go ahead.
So, Claudia, great presentation. I'm curious, and very exciting work. You showed us that you can power the devices, exploiting also this ionic. Is there a way to exploit this type of features to make this less invasive? Right now, you still have to implant the sensor, right? Is there a way to avoid, I don't know, the implantation itself using wireless?
Yeah. Okay. So the thing is, for if you want to record high quality neural signal, it is very important that you can record the activity of a single neuron. And to do that, you have to either go very close to the source, which is the neuron itself, so you have to have this implantable intracortical device, or you can, if you want to reduce the invasiveness, you can just record this activity from the surface of the brain. So in general, one of the good things about these transistors is that, so in general, if you just have silicon-based devices, you cannot record the single neuron activity just from the surface of the brain. You actually have to go in depth. So one main advantage of this technology is that actually you can record such a high quality signal also from the surface. But of course, if you want to record a single neuron activity, you cannot do that through EEG recording because you have the bones and the skull. So you will be able to record neural activity, but it depends how precise you want to be. And for what regards the ionic communication, so as long as you have an ion-rich media, you can transmit the signal in different ways. And also the depth of this transmission depends on what is the size of your gold contact electrodes. Because of course, like in my case, I'm very limited to the size because I perform these in vivo experiments on rodents. But if you go on bigger animal models, of course, you can build these electrodes much bigger. So you can penetrate, you can have this ionic communication for much higher depth. But for answering your question, if you want to have a very high quality signal, unfortunately, you do have to perform a craniotomy. You do have to have your probe that is, if not intracortical, laminated on the surface of the brain.
Mm-hmm. Thank you. Matteo.
Yes. Thank you, Claudia. This was a very good presentation and really exciting work. So congratulations on that. So I want to follow up on the ionic communication for communication and power transfer. And I was curious, how much power can you safely transfer using this technique? And the second question that I had on that is, are there bandwidth limitations? So how does that compare with other, potential, ways of doing this wireless communication?
This is a great question. Thank you for asking that. So for the first question, I was able to power this device by using an AC signal that was about 1 volt. For what regards the bandwidth, there is a limitation. So as I mentioned during the presentation, I really spend a lot of time to try to make this transistor as fast as possible. Since these transistors, they rely on ions, so they can be quite slow. But if I want to establish this ionic communication, I need to overcome the double layer capacitance, because of course, if you put two electrodes in contact with an ion-rich media, you need to be in a frequency that is higher than 1 megahertz in order to establish a communication. So one of the main goals in my research was trying to speed up this transistor up to 1 megahertz so that I could use this ionic communication for both powering and transmitting the signal from my devices. So I'm very glad you asked these two questions because it's something I actually did work a lot to try to optimize. And yeah, thank you.
Thank you.
Any other question?
If we have time, maybe one quick question related to what you just said, Claudia. First of all, congratulations. Great presentation. So you mentioned about speed, and you showed that your devices can measure different types of signals, which I assume requires different amounts of amplification and speed trade-offs. Can you speak a little bit about how this is achieved with this technology? Do you play with materials? Do you play with geometries? Do you play with both?
Yes, thank you, Alberto, for this. This is another very great question. So yeah, so these organic electrochemical transistors are very good for sensing biological signal because they rely on ions. So basically, the transistor channel can kind of like uptakes ion and perform an ionic to electronic transduction with amplification. So while you're recording the signal, you're also amplifying it. So for this reason, these transistors have a very high transconductance, which is good if you want to record low signal quality. One may drawback of this technology, as I mentioned earlier, is their speed. But if you want to have a good signal recording, you need to have fast transistor and high transconductance, so high amplification. The reason is because, first of all, because neural activity from single neuron is in kilohertz. So for sure, you need to have transistor that can achieve the speed, but also you need to have even higher speed if you want to, for example, multiplex the signal. So you want to have you want to have the recording from a lot of channels and then just merge them into one. So this is another thing that I work on a lot. So I changed the geometry and the architecture of this transistor, and I work a lot on the materials so that I could achieve at the same time high transconductance, but also high speed. And that allow me to have this high quality signal recording from single neuron, which is very important because provides a lot of information for neuroscience studies.
There is a question from the chat from Marcello Alecci. How, Claudia, thank you for your very interesting work. Regarding the implanted polymer-based transistor sensors, I was wondering about the stability over time, the biological environment, and the sensitivity, I guess, to environmental radiation.
Yeah, that is another very good question for what regards the stability, because it's another thing I did work a lot during my PhD to optimize. So in this transistor, you have this polymer, which is the transistor channel that is direct exposed to electrophysiological environment. And another drawback was was the stability of this device. People were concerned about that, but I developed a new fabrication and architecture for this transistor so that basically the transistor channel would be coated by a layer of parallelency, so a layer of a thin plastic, while still having a small hydration via for the hydration of the transistor and for the sensing. And this allowed me to have a transistor that had constant transconductance and amplification and was operating nicely for a period of time of 1 year.
Excellent. Any other question? I guess we still have time, right?
No, actually, we finished the time.
Okay, then we should move on. Thank you, Claudia, again, and congratulations on the great work and the career prospects.
Thank you so much.
Thank you, Claudia.
Thank you.
The second finalist is Dr. Michele Cotrufo, assistant professor at the University of Rochester, and this presentation is Engineered Metamaterials for Energy-Efficient Optical Computing and Signal Processing.
1 second. Can you all see the full screen version of the slides?
Yes.
Okay. 1 second. Okay. So thank you for the introduction, and I want to begin by thanks the jury for inviting me as a finalist to give this talk. My name is Michele Cotrufo, and I am an assistant professor at the University of Rochester. And today I want to tell you something about how we can use metamaterials, and I will show you what they are, to achieve energy-efficient optical computing and signal processing. I have a short summary slides to show you my academic and life journey, and I think figures say much more than a few words. So I did my undergrads in Italy, in Bari and Padova specifically. I then moved to the Netherlands for my PhD, and after that I decided to cross the ocean, and I spent a few years postdocing between Austin and New York City. And 1 year ago, a few months ago, I moved to Rochester as assistant professor. So today we are talking about sustainable energy, and of course, when you're talking about sustainable energy, you want to produce energy in a sustainable way, but you also want to use energy in a good way. So essentially, one way to approach the energetic problem of today is to look at what are the dominant sources of energy consumption and see if we can remove them. And nowadays, the biggest source of energy consumption, one of the biggest sources, is the amount of energy that goes into computation and information processing based on digital electronics. So ranging from our own computer and smartphone to data centers and supercomputers. In particular, there are some statistics that actually say that currently the information processing and communication sector consume approximately 10% of the total energy in the US, and even your own Google search typically has an impact on CO2 emission. And so because of this, there is currently a huge drive from researchers in different fields to find alternatives to electronic-based digital computation. And one of them is analog optical computation. So this is just to show you a sort of a schematic of how this works. The idea is to replace electronic as a carrier of information. So rather than having electronic circuits where we inject and process information, we now have sort of photonic circuits where we encode the data that we want to process onto light, onto a wavefront, and then we let it propagate through something that we can call an optical processor. It is going to manipulate this light, the wavefront, and then when we look at a light that comes out of our device, and we look at the information carried by the light, we can extract the desired computation. There are many advantages to this approach. One of them is that if you design your device properly, light will naturally flow this device. So you don't have to push light, you don't have to apply voltages. So this implies that typically you can do this computation with very little energy consumption. And also because you're using light as a carrier, you typically can achieve much faster computation and higher data capacity. So in the last couple of years, we have been working on trying to understand what could be considered the building blocks of an optical computer. And if you try to break it down to basic functionality, you can think about something that I showed in the previous slide. So an optical processor, something that you can send information in the form of optical signals. And then when you look at the lights after it transmitted through the device, you can actually extract information. But you can also be looking into different functionalities. For example, optical router that will steer and reroute signals depending on the information that they're carrying. So the natural question here is, can we actually realize these optical devices that do this task without any energy consumption? And the issue here is that when you actually try to manipulate the flow of light, it's not as easy as manipulating electronics. It's much challenging. And so the key to achieve this functionality is that we need to have access to different materials that are different from the naturally available one. And this is what we call the metamaterials. So as I just mentioned, the general idea is that if you just rely on naturally available materials, you typically have a limited ranges of optical properties, a limited set of refractive indices that you can achieve, and a limited set of functionality that you can induce with natural materials. To go beyond, we use what's called metamaterials, and in this case, the word metamaterial literally means behind natural materials. And the general idea is to still, of course, start from natural materials, like silicon, for example, or any sort of dielectrics, but then we start playing with the morphology of the material. So we start making small inclusions, such as pillars, holes, gaps, that we call meta-atoms. And the trick is to make these inclusions such that they are still much smaller than the wavelength of light that you plan to use. If you use this trick, when light impinges on the material, we'll overall see a general overall response. We'll not see the meta-atoms individually. We'll still perceive your material as a bulk homogeneous material, but now by tailoring the geometry of all of this inclusion, you can actually finely tune the optical response of your material. So let me show you a couple of examples of things that we can do with this approach. So once again, this idea of using a metamaterial as an optical processor, as something that we can send information on in the form of images or temporal signals, and then the metamaterial will perform a calculation of what we send on. The simplest example that we actually have worked in the last couple of years is a metamaterial that can perform spatial derivatives of optical images. So the idea here is that you have this thin layer of patterned materials. You send an image, in this case, just a car, and after the image has gone through the metamaterial, the output image corresponds to the, in this case, second order derivative, or the Laplacian, if you want, of the input image. And the advantage of this is that this mathematical operation, the Laplacian, enhances the edges of the image. So rather than having the full image, in the output image, only the spatial edges have high intensity. And of course, you can imagine that this could have a lot of interesting applications, for example, in the field of self-driving cars, or anywhere you want to simplify what you are seeing before feeding it, for example, to a computer. And of course, the idea here is that if we had such a material that does this, then we could do this computation fully passively, very fast, and in a compact fashion. So we essentially try to understand if this was possible. And the answer is that it is possible to achieve this behavior. But to do this, you need a material that behaves in a very non-trivial way. You need a material that completely suppresses all light propagating at normal incidence, but it lets light propagated at a large angle go through. And this would be very difficult to achieve with just a piece of a bulk material. But what we figure out is that if you start doing this patterning, so in this case, we work with a thin silicon slab, and we realize a periodic pattern of holes, and we carefully control the geometry of this pattern, you can actually achieve this very non-trivial behavior. So then you can go to the lab and check if this works. So we did several experiments with different test images, and the experiment in itself is actually very simple. We have our metamaterial, which is very thin, by the way, is 1/5 of the wavelength. Typically, we send an image on it, and then we look at the image after it. We don't do any sort of other computation. In principle, you put your eye here if you want. And this is an example of what we get. This is the logo of my previous institution. So this is the input image that we send on, and this is what we get after the metasurface. So you get very nicely this edge detection effect, where only the edges of the input image are enhanced. So this is about the spatial differentiation, which can be used for edge detection. You can also wonder about temporal differentiation. So you may want to have an optical element, again, in this case, a very thin metamaterial or a metasurface if you want, such that if you send a signal on it, you want in the output a signal that tells you when the input signal changes a lot. So in this case, we are sending a rectangular pulse, and then the output signal is proportional to the first order time derivative, and it will basically spike whenever the input signal is changing a lot. And you can actually show that to achieve this phenomenon, you need a metamaterial with a very non-trivial transmission spectrum. So it needs to have a transmission 0 or almost 0 at a specific frequency, and then the transmission needs to rise linearly around this 0. So we actually designed this metamaterial and fabricated it. In this case, we used titanium dioxide, but it can be done with many other materials, and we also tested experimentally. So in this experiment, we're sending a square pulse with a duration of about 1 picosecond, and the output nicely enhances the temporal edges. And of course, once you have an element like this that does a certain operation, the nice thing of this device is that being very flat, you can actually cascade them, and you can achieve multiple operations or more complex operations. So in this case, for example, we took 2 of these metasurfaces, each of them performing a first-order time derivative, and we literally cascaded them. It was a very simple experiment. And of course, the experiment confirmed that the output is a second-order derivative. And once again, I want to emphasize that all of these devices, they are passive. We don't apply any bias. We don't dynamically control them. We just literally let light go through them, and then we look at what comes out of that. And then, of course, when you... Yeah, thanks. When you know how to do spatial differentiation and temporal differentiation, you can also think about devices that do spatial-temporal differentiation. So now we have a device that you can send a sort of a video on it, and the device will, the metamaterial will calculate the mixed temporal and spatial derivative of the input. And the advantage of this functionality is that you can do the so-called event-based edge detection. So you can enhance the edges of an object only when the object is moving, which is a very useful functionality, for example, for object tracking. Now, all the devices that I showed you so far, they work very nicely, but they have one big defect, and it is that they are static. Once you make them, they're never gonna be, their functionality is never gonna change. So to overcome this, we started thinking about how we can make some of the metamaterials I showed you earlier reconfigurable. And in this case, what we did is that we took exactly the same metamaterial I showed you earlier for spatial differentiation, and we added a thin layer of vanadium dioxide. Now, this is a very interesting material. It's a phase change material, and it has this property that for any temperature below 65 degrees Celsius, it behaves as a dielectric, but when you heat it up above 65, it suddenly changes to a metal, and so its optical properties will change a lot. So we embedded it in a metasurface, and we actually observe very nicely that, of course, if we fine-tune the design, you can achieve this scenario where for any temperature below 67 degrees, it has the behavior necessary to do edge detection. But then as soon as you cross this threshold, you go back to almost nothing. So in this case, you have a device that by changing a few degrees, around 65 degrees, you can switch between doing edge detection and doing bright field imaging. So of course, still a very limited functionality, but it's a first step forward towards making these devices reconfigurable. So I showed you several examples of devices that do computation. I just want to mention a couple of examples of the metamaterial devices that can do optical routing. And in particular, I want to show you a couple of examples. One of them is the idea of non-reciprocal routers. So now a device, again, a passive, bias-free, a device that does not consume any energy, that allows light to flow only one direction, not the other. And the other device I want to show you is the power limiters. A power limiter is a device that allows light to go through only when it has low power, but when it has high power, it stops it. And you can actually build these devices with bulky hardware, but they, of course, are very energy consuming. And so the idea is whether we can now use, again, metamaterials to realize a passive version of these devices. So I just want to highlight a couple of works that we did in this direction. One of them is, again, the idea of using a meta surface as a non-reciprocal router. So now a very flat device that allows light to propagate only one direction and not the other. In this case, we were able to show it, to do this with a very simple design made of silicon gratings with broken vertical and horizontal symmetries. And another device you can think about is, again, is power limiters, which in this case was achieved by sandwiching multi-quantum wells, which is a material with a high saturable response, between gold patches. So in this case, we realized this metamaterial that behave as a power limiter because at low powers, it reflects, but high power, it completely absorbs. And so you can use it, for example, for protection of sensitive equipment. And once again, everything here is fully passive. So we never have to provide any energy to this device. We never need to provide any modulation. They just exist and they do what we want them to do. So this brings me to my conclusions. I hope I convinced you that the field of metamaterials has a lot of promises in addressing some of the challenges related to the high energy consumption of computation and signal processing. And I showed you a couple of examples related to analog computation. So how you can design metamaterials that literally make mathematical operation on incoming signals. And also a couple of examples on signal routing and processing. So metamaterials that behave in a sort of a smarter way when it comes to reroute light that impinges on them. And again, this is an operation that you will never be able to achieve with just a bulk piece of natural material. And these are all operations that are done passively and without. The nice thing of working in this field is that once you come up with a nice metamaterial, the experiment is very simple because you don't have to deal with applied voltage and so on and so forth. So with this, I want to conclude, and I'm happy to take any questions. I also want to emphasize that I had to go very quickly for time constraint, but if you want to learn more, feel free to either visit our website or feel free to contact me.
Thank you, Michele, for the excellent presentation and the wonderful work. And we have time for questions again, jury or online.
Should I start this time?
Sure.
So thank you, Michele. This is a very, very good presentation, really exciting work. So your point you make on energy consumption is absolutely important, and I completely agree with that. But I wanted to. I was curious in the case of the reconfiguration, right? When you show the vanadium oxide, in that case, do you need to supply a bias to the vanadium oxide to maintain either state?
That's a very good point. Yes, in this case, yes, because unfortunately, vanadium dioxide is a volatile phase change material. We are actually thinking about, and some of the groups have actually done it already, to try to implement the same approach, but now with a non-volatile phase change material. The very nice thing of vanadium dioxide is that the transitional temperature is at a very low temperature. As far as I know, it's the lowest temperature of commonly available phase change material. So that's mainly why we started with that, because we wanted to be able to do the experiment without setting our optical lab on fire.
Yeah. Yeah, I understand. Yeah, but I agree. I think there might be some other materials that could be explored, like germanium telluride or things like that.
The other disadvantage is that the transition between the electric and metal, so when it's metallic, there's a lot of loss, and that really limits the range of functionality that you can induce in the hot state.
Yeah. So, okay, if I can, let me follow up on this. So you mentioned loss, right? And so one other thing I was curious is to what extent you can scale up the complexity of this calculation. So you mentioned that you can sort of cascade multiple layers, but I guess there will be a limit there that due to loss, I would imagine. So I was wondering, did you project, how far you can get with this technology?
Absolutely. So, well, first of all, you're totally right. And it's something that at the end of the day is unavoidable because once again, we are trying to use passive devices. So we can never beat energy conservation, right? So you can actually sort of see already in this plot the level at which we are. Because if you look at the legend here, I have a times 10, right? So this output signal is multiplied by 10 as compared to this. Now, the best you can do in this plot here is to try to get a transfer function that is as close as possible to the ideal one. So you want essentially these edges to go a bit up and this to go down. That being said, in this paper, we actually tried to get a feeling of how bad our devices are. And what we found is that once you fix the bandwidth, and even if you assume an ideal device for that bandwidth, our devices are only 50%, like 1/2, a factor of 2 worse than an ideal device in terms of efficiency, in terms of how much power you get through. And again, this is basically because the main limit here is passivity. So that being said, I totally agree with you that you can cascade them, but eventually you need to decide how much power you're willing to lose. And again, you can see in the cascaded case, you can also see here we have a factor of times 20. So after 2 metasurfaces, we get very nicely the second order derivative, but we lose a factor of 20 in the power. So, I mean, my general sort of pitch about these devices is that they can be very useful, but they're also a bit niche. So you need to think carefully about what is your application. They're not going to solve any issue.
Yeah, thank you very much.
Alberto?
I guess you partially answered my first question, which was the applications you showed are naturally suited to optical computing because you looked at image processing. Do you think there is any path towards making a general purpose machine from this type of technology?
I believe general purpose is going to be very hard. I think right now the main philosophy in the field is to think about it, because essentially I don't think we are ever going to be able to truly beat electronics. What the best we can do right now is to think about dedicated tasks at which optics is better, and then we can think about optical devices that can help electronics. But I mean, based on what I know, based on what's the current status of technology, I think we are still a bit far from a general purpose optical processors or optical computer.
We have one question from the audience. Again, from Marcello Alecci, thank you for being active. Hi, Michele, thank you for your very nice work. Do you have theoretical experimental data about the noise figure of your novel metamaterial-based analog optical processors versus classical digital electronic processors? How do you select the mutual distance in the cascade metasurface device?
Let me first answer the second question. So in this case, actually, this particular device, the distance is completely unimportant. In fact, we also saw experimentally that by changing this distance, we essentially got the same thing. The only thing you want to avoid is to have it so close that you start having a Fariberó effect. So essentially, you want it to be just longer, the gap needs to be just longer than, for example, the coherence length of your pulse, which in this case is very easy because we are using pulses of few picoseconds. So yeah, the only catch in this case is to understand multiple reflection, but you can actually compensate for them. So for example, in this other device, sorry. I talked very briefly about this one, but this one is also actually made by sandwiching two metasurfaces, one making the spatial operation and one making the temporal operation. And in this case, we did have a lot of issue with back and forth reflection, but by doing a fine tuning of the device, we were able to strongly reduce that. For the first question,
2 minutes left.
so for the first question, I'm not sure exactly what you mean by the noise figure. So the general idea is that, as you said, this is analog, right? So everything is continuous. So any noise will be intrinsically assumed as part of the image. And in fact, I think we even have some example. If you look at the, I don't know if this one shows it, but yeah, basically you can see that if you consider this part of the image with some damage as noise, the metasurface does not carry this noise. We could just take whatever comes in and do a differentiation. And you can also see this in the temporal case. Unfortunately, I don't have here the plots I was thinking about, but if you look at the input square pulse here, you can consider this to be noise, and the metasurface will just try to time differentiate this noise. So we're in the realm of analog computation, and I think noise essentially becomes part of the signal at all, in the good and bad sense.
Excellent. Maybe very briefly, Michele, you stressed in your introduction the energy sustainability, that of course it's a topic of this award. That was great. How do you see, you showed us many functionalities that are very exciting and interesting. How do you see this enter into the big picture of improving energy or addressing the energy challenges in applications?
Well, as I mentioned earlier, the key is to look for specific applications where we can replace electronic computation with these devices. And I'm the first one to, sort of say that they're not going to be able to replace electronics everywhere. So an example I made earlier is this one of the self-driving cars, where essentially you can now think about these devices as literal optical filters that you can put in front of a camera and do this computation. So in any scenario where you can think about a dedicated optical task that you would want to offload from a computer, you can probably think about using this approach.
And how far are we from actually integrating this into?
That's also a good question. It really depends on your constraints. I think right now we are still at the beginning of this field, and we're still trying to solve several issues. And as usual, it's a matter of trade-off. So one main issue that we have right now is that in order to do this sort of edge detection, for example, you need some degree of coherence in the illumination. So you still cannot use ambient illumination. There have been some studies where they found a way to overcome this, but then what you are losing is you still need some electronics in that case. You need to do some post-processing. So it's again a matter of trade-off between how complicated you want your operation to be and how much you want to completely give up on electronics or not.
Yeah. Thank you, Michele. Congratulations again on your work and your future career. And the next and third finalist is Dr. Giulia Guidetti from Tufts University. She is Deputy Director and Research Assistant Professor at the Silklab. Her presentation is titled Orchid-inspired solar skins for next generation photovoltaics.
Thank you for the introduction. Well, once again, good morning, everyone. My name is Giulia, and today I would like to share with you a little bit about our recent research program on studying plants that grow in low light and how we can use them as an inspiration in order to design photovoltaic materials. So at Silklab, we often take inspiration from nature. In this case, the inspiration is coming from plants. If you think about it, plants are pretty outstanding because they can grow in a variety of environmental conditions. They can grow in desertic regions as well as in wetlands, under the scorching sun, but also with a little light which is available in the understory of tropical forest. So how do they do that? While green leaves plants, what they do is they take solar energy, they take photons, and they convert it into chemical energy through a process that we know as photosynthesis. And while they do that, they are also purifying the air that we breathe. So now let's take a closer look. If you were to look at the leaves of a regular orchid, one that grows into medium light, this is what you will see under an optical microscope. So on the top of a leaf, you can recognize some of the cells. They do seem to have like somewhat of a regular shape, but there is no large order. There is no repetitive pattern. And on top of that, you can see that the surface is pretty flat. So when light strikes on such a structure, what happens is the light gets refracted inside the material. Then you have a bit of scattering, of course, and then inside the cell, what happens is that you have a photoconversion. So key point is that light gets on the cell and then gets inside the leaf. And this happens for most of the plants that grow under regular light condition. Look at this orchid. In this case, these leaves are green, solid green, no pattern, no particular shape. And if you think about it, orchids are not praised for their leaves. They are praised mostly for their flowers. But now let's have a look at orchids that instead grow where there is little light. So the orchid that we're looking at here now is called Macodes petula, and it belongs to the family of the jewel orchids. They are native to the Southeast Asia, and they grow in the tropical forest. You can see that these leaves are quite different. They are metallic, they have patterns. You can recognize teeny light lenses on top of each one of the leaves. And when you look closer, this is what you see with an optical microscope. This is an image of a leaf in which we can clearly distinguish all the cells. They all seem to have a round shape, roughly a similar size, and somewhat arranged in a regular pattern. But what's important to notice here is the fact that each one of the cells is decorated by this bright spot and bright stripes. So what's happening here is that there is exchange of light from one cell to the next one. So the cells are basically exchanging information. In a way, they are talking to each other. And so this kind of structure can be defined as a living optical network. So what does it mean? Why the plants go through the effort of creating such a structure? What it means now is that since we have a different profile of the cells that are forming the outer layer of the leaves, we have to consider a collective light behavior by which the light that strikes on the leaf does not simply get focused inside the leaf, but a portion of that can be redistributed all over the surface of the leaf. So by doing that, basically the light has more time to interact with the leaf material. And by doing that, we should expect to have a higher photosynthetic efficiency. So why is this important? Why do we care about studying plants that grow in the darkness, basically? We are studying these plants because they are prompting us to ask ourselves both fundamental and applied engineering questions. And the beauty of this is that the question that we can ask ourselves span different fields, from plant science to optics to more technology related. So if you were to take a plant science approach, the first thing that we want to answer is like, what is the actual correlation between the light in which the plants are growing and the order that you see on the leaves of these plants? Optically, we want to know if there is any light trapping. Is there any resonant mode which is occurring inside these dome-like cells? And from a technological point of view, when you see such a system, which is basically a natural photovoltaic cell, well, we want to know if we can actually reproduce it. Can we create a biomaterial-based structure that is able to collect the light and redistribute it in a similar way in which these plants are doing it? So to answer all these questions, we have structured this research program based on 3 pillars: plant science, optics, and technology, with the main objectives of actually understanding what is the structure function relationship that is responsible for this unique optical redistribution mechanism that we see in the jewel orchids. And the aim is actually to basically learn from nature, learn from plants, and apply this principle and transform it into a biomaterial-based interface that can be used not only for solar application, but also simply to guide the light or to encrypt information. So where are we now? Now we are screening plants. We are screening plants that live in low light condition, and we are doing that using a multi-scale structure function analysis. What does it mean? It means that for each plant, what we do is that we start at the macro scale, and then we go down to the micro and to the nano scale, and we study its optical response, its composition, and its structure. And you can see here some of the results, for example, for the Macodes petala, you can see that the leaves are per se a flexible photovoltaic cell. And in the outer layer of these leaves, you can see the cells that have a dome-like structure. And what is important to notice here is that each one of these domes is not only physically interconnected, but also optically interconnected due to the way that the shape of the outer cells has been adapted and evolved by the plants. So when you look at this teeny arrangement of dots on each one of the leaves, they might actually look familiar to some of you because this corona of dots that we see on each cell is basically the fingerprint for cross-communication that you see in liquid crystal arrays. So in the liquid crystal community, what people do is that they build these arrays from scratch, taking microparticles, and then they basically do this in order to encode information, in order to manipulate light using colloidal assemblies. And to build these structures, you need to have stringent conditions regarding the shape of the unit cell, so the morphology, the way each unit is assembled with respect to the other, so the regularity of the lattice, and of course, illumination condition, because after all, we are looking at an optical phenomenon in which light gets collected and then redistributed. So when we saw this array of dots on the orchids, we asked ourselves, is it possible that in a water-based material that grows in the dirt, in the rainforest, basically, we have the conditions that people are striving to achieve in clean room setting? So in order to answer this question, what we do is that we basically borrow computational methods that are typical of colloidal science, and then we apply them to the orchids. So in this case, we use the radial and the angular distribution function in order to assess the regularity of the lattice, if we have any order, long range, short range. And once we know that we have order, we wanted to see which type of order we have. In this case, the control structure is the hexagonal lattice. And in the case of a leaf, what we did is that we started from optical micrographs of the orchids, and then we extracted in a way the corresponding leaf lattice. And by looking at the RDF and ADF functions, what we see is that we are actually able to define order, to recognize order in the way the cells are arranged, short range, granted, after all, this is still a plant. And in this case, in the case of the Macodes, we see that the way that the cells are packed is resembling of an hexagonal pattern. And so now we know that we do have a condition to have an optical network. Next thing to do is basically play with it. And by playing, basically, the question that was driving us is, can we change the coupling condition of the light so that we can modulate how much light is redistributed from one cell to another? So we can do that, for example, by changing the angular width of the light, and by increasing that, you are able to illuminate larger areas of the cells. Similarly, if you are able to access what's inside the cells, the absorbing elements, you can also tune the spectral features of the light, meaning that we can basically modulate the wavelength which get guided on the surface of the leaf. And this is something that the plants are actually able to do naturally because they do have an heterogeneous distribution of pigments all over the surface. Next thing that we are currently working on is basically to see if we can engineer the way that these lattices are grown by the plants. And to do that, we are basically building a living library in which we are tuning the growth condition of the plants. This means that we are tuning the illumination intensity, but also the directionality of the light. And in some cases, we want to see if we can tune the lattice also by exposing the plants only to specific wavelengths of light.
5 minutes.
Some of the adaptations that we expect to see are in the shape of the cells, in the regularity of the lattice, and also in the concentration of the photosynthetic centers. And of course, when you have a system like that, as I mentioned before, you want to replicate it. In our case, the material of choice is silk. Silk fibrin is a protein which is naturally produced by the silkworm. And what we do in the lab is that we start from silk cocoons and we transform them into a liquid solution that then can be used for a variety of applications. Why silk? Because it is a sustainable material that can be sustainably processed. And specifically for this project, the importance is the fact that it can preserve biofunction. So you can basically dope these leaves, these replicas, with photosynthetic elements. And it also has nanoscale conformability, meaning that we should be able to reproduce the pattern that we see in the orchids. And indeed, we have been able to do that, as you can see here, both from the optical analysis and the morphological one. We are able to see the same pattern that you see on the orchids, on silk replicas, with enhanced distribution of the light all over the surface of the film. Next step for us is to dope these materials with photoactive elements. We started with fluorescent dyes, and then see how they behave once we integrate them with actual optical and electronic devices. So with this, I hope that I shared a little bit why you are looking at plants that grow in the dark, how we are looking at novel ways of redistributing the light that were not described before for natural system, and now we can use them as an inspiration to fabricate sustainable solar skin that can be conformable, can be produced at large scale, and that can be stable over time. And with this, I would like to thank you for your attention, thank everybody at Silklab, and especially my mentor, Professor Fio Menetto.
Thank you very much, Giulia. Another excellent presentation and wonderful work. Again, we have time for questions, both from the jury and from the audience.
Okay, this time I start then. Thank you, Giulia. Really great presentation. Actually, this is a perfect slide where you talk about solar skins and optical networks to process and control light. Can you sort of compare and contrast this approach that is biomimetic versus what would be a more engineered approach with very well-defined materials and shapes, and why one would prefer one versus the other?
Well, in this case, we are starting from something which has already been optimized by nature. So the main advantage will be to use a material that already is performing both like focusing of the light inside the leaf and redistribution on the plane. So we already know that these plants optimize the structure because they are growing where there is very little light. So main advantage is that instead of going through an optimization process, you can start for something that has been pre-optimized in a way. The other thing is that the other way is that we can basically directly fabricate the skins by replicating on the living structure, and we can use biomaterials. This is a very important point for us because all this structure, you can make them out of silk, and you can make out something that can already be produced at scale, and it is fully water-based. Does this answer the question a little bit?
Yes, thank you.
So Giulia, very impressive, inspiring that one can take lessons from biology and how it self-optimizes. Maybe one follow-up question is how much biology and the plant, I guess through evolution, has found its way to optimize certain functions that are crucial for its own interests. To some extent, you showed us, I believe, how you can control this through illumination, through wavelength. How far can you push it? Or what range of control do you have over this, both here and in the silk approach?
So, okay, it depends what you want to push. It's like if you want to control the wavelength selectivity, like the light guiding, that depends on how you dope your material. So in the plants, you already have natural pigments. So you have chlorophyll, you have a lot of like anthocyanins as well that can absorb different wavelengths of light. So in nature, you are limited. Your background conditions are given by absorbing pigments. In the silk, as far as it's water-based, you can dope it. So you have basically, I would say, a water-based infinite library to play with. In terms of like light propagation, So how much you can basically have a light going from one cell to like 3 cells over? Well, that depends on quite a few factors, actually. It depends on the shape of the cells. So, and it depends on the order of the lattice. We see other plants that seem to have dome-like structure, but not so much. And so you have a bit of cross-communication, but then like is not as much as in this particular species. And the third parameter, which we found to be crucial, is like what's the background on which the domes are placed, because you need to have a bit of curvature in also to basically have a light go to like the 5th or the 7th cells. If it's just flat, in that case, you go to the 2nd and the 3rd one. But you can tune it, for example, by inducing total internal reflection if you were to flood the outer layer with another liquid so that you can have a light jump further away.
Okay, excellent. Thank you.
Yeah. So thank you so much. This is, again, an excellent talk, really interesting results and inspiring, really. So congratulations on that. I wanted to follow up a little bit on both questions that were asked before. And I was wondering if there are, some specific device metrics or application metrics that you think this approach could improve.
Well, think about like solar farms. They're placed in the desert, in desertic regions where you get most of the sun, because you need to get a lot of light in order to have higher efficiency. In this case, due to the fact that all the light that is striking on the leaves can also be redistributed on the plane before being focused inside, basically enables to be more efficient in the collection. So to answer your question, I will say that one obvious application for us will be to basically use this kind of solar skins where there is not so much light, so you can get the most out of that.
Thank you.
Thanks.
There is another question from Marcello Alecci. How, Giulia? Thank you for your very nice work. Based on your literature, it looks you are patenting these 2D, 3D optical networks. Of course, considering confidentiality issues, please could you provide some technological developments about your discovery inventions?
Tricky question to answer since this is recorded. Well, I will say that the key points here are in being able to replicate such a structure, in being able to produce it at scale. If you were to take any material, you wouldn't be able to actually get such a patterning out of a leaves. Here we're talking at the micro scale. I have not mentioned any nanoscale feature, which, considering that we are looking at a material like cellulose, which is from the plants, which is intrinsically birefringent, that can play a role as well in the pattern that we see optically. So I will say that material-wise, to replicate and the ability to fabricate such a material at a large scale. Happy to answer more when it's not recorded.
Maybe in Washington. Any other question from the audience or So the aspects that you are actually protecting in terms of IP is more the fabrication and the scalability, not necessarily the application.
2 minutes left.
Or also in the application side.
Yes.
Very good.
I have one last question since we have a minute. So you talk about silk, now you talk about cellulose. What other biomaterials do you think would be of interest in this space?
I will see, depends what you want to do. If you want to directly interface it with a plant, you want something which is water-based. You could try, for example, chitin derivatives, but you also need to have something that you can easily tune the viscosity so that you are able to reproduce all the features that you see in the plant. And it needs to be transparent so that while replicating the structure, you're not basically obstructing the physiological function of the plant itself.
What about organic and inorganic composites? Do you think that'd be a possibility too?
It can be, as far as it does
Minerals.
not damage the structure. You might be able to replicate it also with that. We have not tried playing with that yet, but it's a good tip. Thank you.
I think we're right on time. I would like to say that we have a really great prospect in terms of future, seeing how good these young Italian scientists are doing and the prospects they have in the future. This has been a very impressive symposium. I would like to close the symposium to ask Cinzia Zuffada to say a couple of words.
Thank you, Andrea. Let me start by congratulating the finalists. It has been a set of 3 excellent talks delivered with enthusiasm on topics that are very important and very attractive. Let me add, in the spirit of the Strazzabosco Award, this is our second longest running award, right? It's second only to the Campese Award in the life sciences, to recognize the richness in the community in the physical sciences. And we have a history here of having identified and recognized really, really excellent people. And you are among them. So I can appreciate that the jury will have a difficult time now that they need to sit down and select a winner out of this. I want to thank the jury for all the work that you have done in evolving this set of 3 very meritorious research types. And I'm sure that the Strazzabosco family is extremely happy with this outcome. Professor Strazzabosco has not been able to attend the presentation. He normally does that. I know that it's a very busy time for him, but is looking forward, as all of us are, to meeting the finalists in person. And I can give you a preview of the coming attractions. There has been, upon impetus by the family, the development of a book that celebrates the more than 10 years of Strazzabosco winners. And so the book is being printed as we speak. There will be a series of copies at the embassy. You will have the opportunity to pick up your own copy. There will be a celebration around the award with a strong show and the history. You will be part of that celebration. So be prepared. And I really look forward to meeting you in person. And the symposium is now coming to an end. Thank you, everyone, for participating.
Thank you and congratulations again.
Thank you.
Thank you. Yeah.